On October 14, 2025, a colossal machine pointed toward the heavens from a coastal launch pad in South Texas. This was SpaceX's Starship, the final iteration of its version 2 design, undertaking a crucial uncrewed test flight. Its mission was ambitious, yet simple in its cosmic audacity: to ascend to the edge of space, to circle a portion of our planet, and to return through the atmosphere to a controlled splashdown. This was not just another rocket launch. It was a test of a vehicle designed to fundamentally rewrite the rules of space exploration. Hours before the sun graced the horizon, the launch site was a hive of controlled, focused activity. This was the pre-launch phase, a period of profound tension where every action is deliberate and every second is accounted for. Engineers, huddled over consoles glowing in the dark, were the sentinels of the machine. They meticulously ran through checklists, verifying the health of thousands of systems, from the complex avionics that serve as the rocket's brain to the simple valves that must open and close with perfect timing. Fueling began, a process that is itself a monumental feat. Cryogenic liquid oxygen and methane, colder than anything found naturally on Earth, began to flow into the vehicle's massive tanks, causing the rocket's thin steel skin to creak and groan as it contracted. The mood was one of professional calm, a practiced stillness that belied the immense energy coiled within the vehicle. Onlookers, gathered at designated viewing areas miles away, felt a different kind of tension, a blend of excitement and apprehension. They were witnesses to history, regardless of the outcome. The countdown clock, displayed on giant screens, is the impartial narrator of this phase, its numbers marching relentlessly toward the moment of truth. As the countdown entered its final minutes, the process became largely automated. The human role shifted from active operator to vigilant observer, ready to intervene if any off-nominal readings appeared. The go-no-go polls were conducted, a final call and response where each director confirmed readiness. Propulsion, go. Avionics, go. Range, go. Each affirmation was a small victory. Another gate passed on the path to liftoff. The venting of excess cryogenic gases made the giant machine look alive and breathing, impatiently waiting to be unleashed and fulfill its destiny. In the final minute, a powerful water deluge system activated, flooding the launch mount. This was not for fire suppression, but for sound suppression. The acoustic energy from 33 Raptor engines is so violent it could tear the rocket and the pad apart. The final seconds ticked away. 10, 9, 8. At this point, there is no turning back. The rocket is committed. The hopes, the engineering, the years of work are all riding on the next few moments. The ignition sequence began with a flash of green, the signature of the chemical igniters. Then, the Raptor engines roared to life. In a rapid, staggered cascade, a volcano of fire and smoke erupted from the base, engulfing the launch mount in a maelstrom of controlled violence. For a heart-stopping moment, the colossal vehicle remained tethered. The ground shook for miles around. A rumble felt as much as heard, a vibration in the very bones of everyone watching. Then came the moment of release. The clamps retracted, and the 25-story machine began its ascent. It rose with a deceptive slowness at first, the sheer scale apparent as it cleared the launch tower. A deafening, crackling roar that overwhelmed the senses. The brilliant column of fire painted the sky in orange and yellow, a man-made sunrise, a titan wrestling with gravity, leaving a temporary scar across the morning. The rocket pushed through the period of maximum dynamic pressure, or max-Q, where velocity and atmosphere exert the most extreme stress on the structure. Starship version 2 endured this trial, its stainless steel skin holding firm. It reached for the thinner air of the upper atmosphere, engines burning with ferocious intensity toward the stars. Following Max Q, the mission entered stage separation, among the most hazardous maneuvers. The booster had to shut down and detach as the upper stage ignited to continue the journey. On this flight, the separation was not perfect. A slight wobble in the cosmic ballet. The booster targeted a boost back, re-entry burn, and gentle splashdown in the Gulf. Telemetry showed control issues during descent through the atmosphere. It did not achieve a soft splashdown, meeting the ocean in a hard, likely destructive impact. Meanwhile, the upper stage pressed on, engines throttling in sequence as one showed anomalous behavior and shut down early. Others compensating while controllers watched the numbers with caution. The ultimate goal was nearly one full orbit before a Pacific re-entry. But an early engine shutdown and a suspected propellant leak meant orbital velocity would not be achieved. Controllers ended the flight plan early, shifting to gather as much data as possible. This is the nature of a test flight. The plan guides. Physics decides. At hypersonic speed, the vehicle met the upper atmosphere. Furnace-hot plasma formed. Onboard views were breathtaking, then alarming. Signs of tile damage. Several tiles broke away, exposing structure to punishing heat. A cascade followed. Telemetry indicated loss of integrity in a forward flap. The spacecraft began to lose stable control in the upper atmosphere. The mission ended not with a gentle splashdown, but with breakup over the ocean. From an engineering perspective, it was a treasure trove of data. A clear record now shows how, where, and why Starship-2 failed, pointing precisely to improvements. So why does this specific flight matter so much, especially when it ended in a fiery breakup? Progress in rocketry is iterative. We learn by doing, and often by failing. Even the Saturn V was forged through years of tests, including explosions on the pad. This full-scale systems test pushed beyond simulation, revealing hidden weaknesses. Hot staging data refined separation stability. An early engine shutdown informs Raptor reliability. Heat shield failures give direct answers about design and application. Engineers now know what failed first, under what conditions, and how to redesign tiles, adhesive, and structure. A hardware-rich approach: build, fly, test, iterate, fast. The factory in South Texas is already preparing Starship version 3. Accepting some failures accelerates innovation in a field long defined by caution. Each test, success or not, advances a multi-generational project toward the Moon and Mars. Big dreams require bold attempts and the will to risk failure. The next launch stands on these lessons, one step closer to the stars.